Okay, so now my recording has started. So now let's understand the mathematical concept of the angle modulation. Uh, so uh, I use this thing. Uh, so if I have angle modulation, which I don't write AM because AM is normally used for the amplitude modulation. So I will use the word your uh, modulated carrier. Modulated carrier is means either AM or FM is represented as, because that depend upon the what type parameter I'm varying. XCT, let's say, is equal to VC cos theta t. Okay. So my modulated carrier means the final modulated signal. Okay. So here my XC could be FM or PM, as I said, VFMT or VPMT, but generally it remains VC cos theta t, where VC is your maximum amplitude of the carrier signal, as we have seen earlier. It remains the same, but now we will not vary this parameter. We have to vary in this one, and theta t is equal to omega ct plus phi t. Okay, that we have seen, and your so omega c is your carrier frequency, angular carrier frequency. Okay, and phi t is your, so phi t we call as instantaneous phase deviation. Instantaneous phase deviation, okay, or phase angle. Because phase is always measured with respect to a certain angle. You can't measure the true phase. So it is always a phase deviation we measure. Because suppose I'm sending a signal, there is automatically some phase is there, inherent phase. It could be 0 degree, it could be 10 degree, it could be 12 degree. So how much phase is deviated? So phase is always expressed in terms of the phase deviation. So it is a phase angle. So how much is varied? And obviously, which is a function of the modulating signal, which is my message signal, which we keep as same as we have discussed the last time. That is VMT is equal to VM cos omega MT. Okay, so this is the one. So here it is defined as instantaneous phase deviation. Okay, so just like we have instantaneous phase deviation, I can define the instantaneous angular frequency, and that is given by, so we define this parameter. So I'm just highlighting various things what we are learning here. So this is the instantaneous phase deviation, phi t. Okay. Now we talk about, go back to the previous slide. Now we talk about instantaneous, how phase and frequency are related to each other, radian, or sometimes we say radian frequency also, or angular frequency, or simply frequency also. So it is given as omega I t is equal to d theta t by dt. That is how the frequency and phase are related to one another. That is d by d theta by dt. Or I could write down this as d by dt of omega ct plus phi t. That is what we have seen earlier. Theta t is represented by omega ct plus phi t. Or it is given as omega c plus d phi t by dt. So that is how I define my instantaneous radian frequency or the angular frequency. So this is how we define this. When phi t is constant, so what will happen? Your d phi t by dt will be equal to 0. So you are left with omega I is equal to omega c. Omega c is nothing. It is equal to 2 pi fc. Okay. So it is quite obvious when there is no change in the phase deviation. That means phi t is constant. Your d phi t by dt becomes equal to 0, and your omega I becomes equal to omega c. Okay. Then we have another important point to be noted, which is I put in the black color. Okay. In frequency modulation, so both the things we are doing simultaneously. Instantaneous frequency, which could be frequency of carrier is proportional to instantaneous value of modulating signal. Value means amplitude of the modulating signal. That means d phi t by dt, okay, which we have just quoted. So I could say that what it implies. It implies that your d phi t by dt is equal to some constant kf. Let's say I have defined this constant vmt. Okay, where I am defining kf. So this is how we defined the frequency modulation. Okay, so in frequency modulation, your instantaneous frequency of the carrier, okay, that is frequency at every instant of the carrier, is proportional to the instantaneous value of the modulating signal. And this is my modulating signal. So it is, I could write this as d phi t by dt, okay, as kf vmt, where kf is, so there are certain parameters which we have to know. Deviation constant, some constant multiplied by the master signal, and is expressed in terms of the radians per second per unit of VMT, obviously. And therefore, I can express a FM signal can be expressed as, now I'm actually saying this XCT as VFMT, just like we have VAMT, VFMT. So this is very important, is equal to VC. I'm not changing this parameter. I'm not changing this parameter. I'm changing the only the frequency part. So cos omega CT plus KF VMT. This to be noted, because we have seen that KF VMT is nothing, is it was equal to d phi t by dt. Okay, so frequency is nothing. It is d phi t by dt. Okay, the phase is changing. So my amplitude remains the same, VC. Here I'm not playing the VC term. Last time we changed the VC part, but other part remain the same. Now I'm playing with the angle part. And the frequency modulation, my frequency which was carrier, it is now changed in accordance with the master signal, VMT. So there is a deviation constant which we define KF as d phi t by dt. Okay. And similarly, if I have to define the phase modulation, which is also equally important, on the same line as we have just discussed, instantaneous phase of carrier is proportional to instantaneous value of modulating or master signal. Okay, that is, I could say phi t is equal to kp vmt. Okay, so this is we got it from this one, kf vmt, for the frequency modulation. So just like we have defined the frequency deviation here, okay, I defined the phase deviation here. So this is on the same line. So both we are doing the thing simultaneously. Now, where my Kp is known as phase deviation, just like we have defined Kf as the frequency deviation. Okay, and it is expressed in terms of radians per unit of VMT. Okay. And therefore, just like we have expressed the FM signal in this form, VC cos omega CT plus KF VMT. Okay. So I can mark the same lines. We can go for that. Your PM signal can be expressed as, how it can be expressed as VPMT. Remember that carrier remains the same, cos omega CT plus KP VMT. So it is in terms of the phase deviation, and similarly the other one was in terms of the frequency deviation. 1 minute. So this is how we define this phi t. This is nothing, as you have seen, it is phi t. So this was phi t. In the previous case, this was d phi t by dt. That means is a function, a frequency, okay, in the frequency deviation, and this is a phase deviation. Let's do certain example, because to understand this thing better, I think there is some disturbance. Somebody has switched on his microphone. Okay, fine. Yes.
Sorry, sir, but can you go to the previous slide?
Yes, yes, please.
Sir, KFVMD shouldn't be added to omega C because both have different dimension.
No. See, both have different dimension. That is the angular frequency multiplied by the time. Okay, and this is KF is a constant, deviation constant. It has also got certain units. I will explain to you. Just wait for that. Okay. It is not KF is not a simply constant. It is also has got certain unit. Just wait for that. I will do the example based for clearing this part. I was coming to that. Okay. So let's. It is a good question. Let's take this example just to understand how these things happen, how these units and all those things are going to be there. So let's take one example, which I put it as. Okay. I have got a angle modulated signal. Let's say I don't define what is that. So I got an angle modulated signal, which is given as XCT is equal to 100 cos 400 pi t plus pi by 4. And I have to find what is the instantaneous frequency, which is Fi. That I have to find. So to solve such thing, let's understand. Now we'll get the idea clearly how the units are expressed here. So this is the thing, and if we know that your XCT is given as VC cos theta t, and if I compare these two, what I get it that your theta t is equal to 400 pi t. Just see this thing. Now you'll understand why my angles and units are same. So it is 400 pi t plus pi by 4. And this is the one. And if I have to find the instantaneous frequency, so first we find the angular frequency, which is given as omega I is equal to d theta t by dt. Okay, that is how we have to find the omega I. So it is, in this case, it turns out to be d by dt of 400 pi t plus pi by 4. So it means your omega I is equal to 400 pi radians. Okay, so you got the same thing. There is no problem with the unit here, and which means, okay, I will put it here. Your 2 pi Fi is equal to 400 pi, which means your Fi is equal to 200 Hz. So there is no problem with the unit. We got the answer in Hz. So your angular modulated signal is given by theta t. So that means this thing, cos 400 pi t plus pi by 4 is my theta t. And I have to find what is my angular frequency or instantaneous angular frequency or instantaneous frequency only, which is 2 pi fi. So here it is just take that d by dt, and now you see that there is no problem with the unit. We'll come to that. Now we'll talk about the phase modulation also in the later example. So as I said, we are dealing simultaneously, but now let's split. We understand one by one. We'll start with the FM, and then we'll go to the PM. Though I said both are related to one another. One is the indirect FM. Okay, that means you are changing the phase, so you are getting the frequency. d phi by dt is equal to the frequency. So rate of change of phase is nothing, it is your frequency. But now we'll talk about a simple frequency modulation. So let's just start with the FM only, and then we'll go to the PM also. So FM. So that we have already understood, it is the form of angular modulation in which your instantaneous frequency of the carrier is varied in accordance with the instantaneous value of the modulating signal. So it is simply, I would say, I am writing it again for you. So it is the angle modulation, because now we are dealing separately. In which, just you understand, the frequency of carrier is varied in accordance with instantaneous value of the modulating signal or the message signal. Okay, so that is something which you have done, written again and again. So if VMT is equal to VM cos 2 pi FMT, which is nothing, 2 pi FM also we have known that it is omega m, then we have seen that VFMT is equal to, we can write down this as VC cos 2 pi FCT, which is the carrier frequency, okay, plus MF, just like we have a modulation index for that. So here also we define the modulation index, sine 2 pi FMT. As in the case of the AM, we have the modulation index there. So here we define MF as the modulation index, because that is important, how much I am modulating the signal. So here also depth is important. So on the same line as we have done for the amplitude modulation, I can define this one. So the carrier plus MF sine 2 pi FMT. So this is the modulation index of the FM signal. Okay. So let's do what will happen. How my modulated frequency modulated waveform will look. If you recall, my AM signal was looking like this. So just leave it at this place. How it was looking? This was my message signal. This was my carrier signal. And if you recall, my modulated AM signal was looking like this. So there was, okay. So where there is a maximum, I got maximum. Where there is a minimum, I got minimum. My frequency of the carrier remains same. So here, my frequency of the carrier remains same. But amplitude of the carrier changes with amplitude of the message signal. So here, if you see, I am getting the maximum here, maximum amplitude. So I am getting the maximum here. I am getting the maximum amplitude. So I am getting the maximum here. I am getting the minimum here. So I am getting the minimum here. So frequency of the carrier remains the same. That is, it is varied in the same this thing, but my amplitude is varying. So if you see, the AM wave means amplitude modulated wave. So if you see, the amplitude is changing. It is taking a trapezoidal pattern, what we see in the oscilloscope, or a fish type of the thing. That means you're getting maximum, minimum, maximum, because my message signal is also varied, maximum, minimum, and minimum. But how my FM signal will look? Oh, 1 minute, please. Hello. Yes, yes. Huh. Yes, yes. Tomorrow? 11 to 1. 11 from 11 on tomorrow. Huh? Okay. Yes, yes. You please send me the link. Huh? Sorry. So, how my graphical presentation of FM wave looks? So, to see to that, I draw it very clearly. So, we go for the just like we have seen for the AM. But here I am expecting my amplitude will not change, but the frequency will change. So for that, I put it something like this, a graph. Let me draw very clearly. Okay, I think this is fine. And then I have it here, I have it here, and I have it here. So let's draw with the first one, which is what we call the uh, modulating signal, because everything varies in accordance with that. Okay, which is your VMT. So let's draw. It is a low frequency. So it is a low frequency signal. So I draw it very low frequency that it goes like this. It goes here. It goes here. It goes here. Oh, sorry, I draw it slightly better way because I want it put in one slide. So I have to keep the so let's mark or something like this also. So I start with this. Now let's draw a message signal very clearly. It goes here, then it goes here, then it goes here, then it goes here, then it goes here, and this one. Okay, beautiful. Okay, so this is my message signal. Okay, now here we don't have any signal. Okay, no signal. Here, if you see, I term as zero crossing because it is crossing the zero line. So this points, we are talking about the zero crossing. This is what we call the as negative slope because my slope is decreasing, and this we call as positive slope because my slope is increasing. Okay, so I've defined various points just to show you clearly how my FM wave looks like, how my amplitude of the carrier is varied in accordance with this signal, which is my message signal. So I define various points. At this point, there is no signal. This point I defined as zero crossing point because it crosses the zero. This side point we defined as negative slope because here my slope is decreasing. And such things we define as a positive slope where my slope is increasing. So this is the point I can call as maximum negative slope. And this we call as what we call as maximum positive slope. Okay, I hope it is, I'm writing very clearly here. So maximum negative slope will be here. Okay, and maximum positive slope will be here. Okay, 1 minute. I remove this. So these two are the points I'm defining. So this is my message signal, a single frequency. And then we defined a carrier. Carrier, I take a green line. So carrier is a high frequency signal. Let's say my carrier is a high frequency signal. So it is a single frequency carrier. So this becomes my a carrier or a high frequency signal. Okay, because here time period is very small between two, so it is a frequency is very large. Here time period from this to this is very large, so frequency is small. So this is my carrier, which is unmodulated signal, unmodulated carrier. And then we define the with the usual color my FM wave, FM or modulated carrier, frequency modulated carrier. How it will look? So if you see here, in this range, I don't have the uh, no signal. So here my signal will remain the same. So here my carrier will remain the same as we have seen here. So there is no change because no signal. So only thing the carrier remains the same. Now here there are certain points. Here I am getting the maximum negative deviation. Maximum negative deviation because we are talking about the frequency deviation. And at this point we'll have maximum positive deviation. Again, maximum negative deviation. And similarly here, maximum positive deviation. Now it is maximum negative deviation means my frequency, the amplitude should not change. Amplitude should not change. So amplitude is going to remain within this. Amplitude is going to remain. I draw with the same color rather than amplitude of the carrier will remain the same. Only my frequency is changing. Okay. And frequency deviation is changing. The frequency could be minimum or maximum. So here, now if you notice here, this is the maximum negative deviation. So my frequency will become smaller than the original carrier frequency. Okay. And here also, I got a maximum negative deviation. So my frequency will become smaller than the carrier frequency. And it is a maximum positive deviation at this point. So here my frequency will be like this. And here my frequency will be like this. So you can clearly see this becomes my frequency modulated. Because if you see here, how my frequency is decided by this, because we are varying with the time here. Okay. No amplitude is not changing. Previously, if you see in the last slide, my frequency remains the same. It is exactly the same as the carrier. Okay. But here, my frequency of the carrier is varied in accordance with the message signal. So wherever we have the maximum negative deviation, okay. So if you see my frequency has become less, so this becomes more, and this is for my original carrier. So here I get what we call the frequency is less than the carrier frequency. Here it is in this range, I get frequency is greater than the carrier frequency. Again, frequency is less than the carrier frequency. In this range, frequency is greater than the carrier frequency. And in this case, in this range, because there was no signal, I have the frequency as the carrier signal. So this is the frequency of the modulated carrier. Now, if you clearly see, when there was no signal, I just get the carrier, okay, with no change. That means my frequency of the carrier remains the same. Here, my frequency has become smaller because there is a maximum negative deviation. Here, there is a maximum positive deviation, negative slope. If you see, it is going here, so it is increasing. So here, my frequency has increased, again decreased, again increased. So there is a change in the frequency of the carrier, no change in the amplitude of the carrier. So this becomes a frequency modulated signal. So suppose I gave you two signals, one which look like this and other which look like C. By naked eye, I could easily say this is an AM because my amplitude is varying. The frequency remains the same as the carrier. Here, so I can say in this case, your F is equal to FC. Okay. This is the carrier frequency FC. No change in the frequency, only the change in the amplitude of the carrier. So this has become my modulated carrier, FM modulated carrier. Here my amplitude remains the same. Please note that amplitude remains same. And that is what we should expect, because amplitude we are not varying. So this becomes my graphical presentation. I think I have drawn very beautifully, otherwise very difficult to understand. And so this is the graphical representation as compared to the AM. PM will do this separately, as I said, because it looks also slightly different. Obviously, in the PM, which is a function of the frequency also, we'll see how it will look. But right now, I'm just discussing the FM part. Okay, so we have discussed the frequency modulation waveform and other things. So one, we have got this definition of VFMT is equal to VC cos 2 pi FCT plus FMT in terms of the modulation index. So I put it in this bracket. So this is in terms of the modulation index. Okay, but what is the effect of the modulation index? We'll see, discuss later on. So there is one way of expressing the FMT is this one. Another way which we have seen earlier was this fashion. So in terms of the deviation, it is given by this. So let's mark this expression as A, and which is in terms of the deviation. Okay, KF, instantaneous deviation constant, KFT. So KF is a deviation constant. Okay, where I've written somewhere. Yes, frequency deviation. Somewhere I've written deviation constant. KF. Yes, KF is known as the deviation constant. So this is the expression for FMT. A modulated FM modulated signal, VC cos omega CT plus, that is in terms of the deviation constant. And this is the another one which we just got it. It is in terms of the modulation index, the frequency modulation index, MF, and we'll understand this thing. Okay. Okay. Now we'll introduce just to understand what was the question also. It will be clear, very clear, all those things. So we'll understand the next part, which is, again, I put in this one, concept of instantaneous frequency. So many terms are there: instantaneous frequency, frequency deviation, and everything. So, which I say as a function of the instantaneous frequency of FM wave. So we are just continuing with the FM wave only. Okay. So it can be written as F of FMT is equal to frequency of the carrier plus the KF VMT. Okay. How we got this thing? That I'm seeing from the equation number A. Okay. If you see this equation number A, which I just go back to the slide so that you can look into that. This is the one. Omega CT plus KF VMT. Only now, instead of omega, I'm using the 2 pi f. So when you're talking in terms of the frequency, so it becomes FC plus KF VMT. Okay. So this is from this expression. So instantaneous frequency is given by this one. What is this instantaneous frequency? As I told you, this is my instantaneous frequency. At every instant, every instant it is changing. Okay, so here it is my instantaneous frequency is this. Here my instantaneous frequency is slightly higher. Here my instantaneous frequency has gone down. And here my instantaneous frequency is the same as the carrier. So that is how we define the instantaneous frequency. In mathematical form, the same thing could be written as from equation number A. It is straightforward, where we know VMT is nothing. It is VM sine 2 pi FMT. I think that you must be knowing, either somewhere I'm using omega m, but sometime I'm using 2 pi FM. It is fine. There's no problem. So it implies that F of FMT is equal to FC plus KF. Sorry, this is a subscript. VM sine 2 pi FMT. Now here we define a parameter, what is called a peak frequency deviation. This parameter we define as, which I showed in the slide also, delta. So this delta is defined as peak frequency deviation. If you recall in the previous slide, I used this word: maximum positive deviation, minimum positive deviation, maximum positive deviation. That means the peak frequency deviation. Okay. So this is that what I defined here as the maximum negative deviation, maximum positive deviation, and so on. Okay, so that is my uh, deviation. So here I defined that thing mathematically, what we have seen in the graphically. So what is this max peak frequency deviation? We defined as maximum change in frequency on either side of carrier frequency. That it could be positive or it could be negative, and that is how we define KF. Okay, why it is the maximum? Because uh, carrier frequency is equal to KFVM. Why? Because your maximum value of sine is 1. So it remains KFVM. So delta defines as the peak frequency deviation and given as KFVM. KFVM. So that is what we call a maximum frequency deviation. And therefore, I can express my FM can be expressed as another form. And that is what we call F of FMT. Oh, sorry. I removed this, not FMT. F of FMT is equal to FC plus del sine 2 pi FMT. Okay, so that is in terms of the peak frequency deviation. So I could express my FM signal in terms of the modulation index given by B, in terms of the deviation constant KF, and also in terms of the this peak frequency deviation. Okay, so this is the expression of the frequency of the FM signal. Okay, so this I write it like this. So if you see, my frequency is now changing as per this FC plus delta sine 2 pi FMT, and delta is my deviation. It could be negative and all those things. So here we defined another parameter, what we call the carrier swing, because that we normally see when we do the practical experiment. So I write it clearly. Carrier swing is a very popular word which we normally use in FM. So carrier swing is nothing. It is basically, it is 2 delta, twice of delta, the peak to peak frequency deviation. Now, if you see here, my carrier swing will be from peak to peak, from here to here, from here to here. So that becomes my carrier swing, because carrier swing is simply nothing. It is what we have just learned. It is what we call, it is peak to peak. That means maximum to maximum or minimum to minimum. Peak means maximum or minimum. Peak frequency deviation. That is, your carrier swing is equal to 2 delta. Okay, and delta is defined as KFFM. So carrier swing is nothing. It is basically your peak to peak. Remember that I am saying again and again, peak could be maximum or minimum. Okay, so either you take minimum to, so carrier swing, just like a swing goes here na, from maximum to minimum and then again to maximum. So this is like the same way. So it is a very common word we use in this one. So it is defined as, it is also, we can say, it is the total variation in frequency of carrier signal from minimum to maximum value. Okay. So this one, this is the, let's do one example again based on what we have done. So we have learned the three equations, one for in terms of modulation index, in terms of the deviation constant, and just now we talked about the frequency where we introduced a parameter frequency deviation. Let's do one example now. Okay. Uh, I have got a, let's say, a modulating signal. Modulating means it is very clear. I am stressing again and again. It is a massive signal or a low frequency signal. Let's say it has got a instantaneous value of 150 millivolt. Okay. And it modulates. Modulate means changes the frequency of carrier signal, which is given as Fc is equal to 100 megahertz. And also it is given as the deviation constant of FM modulator is Kf. Okay. Kf is the deviation constant, which is given as 30 kilohertz per volt. Now, somebody asked me that the units are not matching. 1 minute, sorry. Hello. Mm-hmm. 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 Uh, hello. Uh, okay. Sorry for that. So basically, 1 minute. Let me come back to the screen. Yes, my Jamboard is visible. Sorry for that. Is my Jamboard visible?
Yes, sir.
1 minute. There is my okay. Am I audible? Am I audible? Is my screen visible?
Yes,
Okay, okay.
yes, sir, yes.
Okay, fine, fine. So now if you see here, somebody was asking the units. So see, deviation constant is expressed in terms of like this, kilohertz per volt, because it is per unit of the message signal. And if you put these units, you will get the answer. So basically, it is like this. Sorry. Hmm. Okay. So now we have to find what is my output signal frequency of the resultant wave. Okay. So the question is, I put it here. We have to find output frequency of the resultant FM wave. So how to solve this problem? So we go to the next slide to solve this. So if you recall, it is given as FFT, that is my output frequency, which is given as FC plus KF Now in this case, what we have got it, if you go one, we have got the FC is given to be 100 megahertz, KF is given to be 30 kilohertz per volt. So it will also clear the doubt, this example, as I told you, regarding the units and so on. And VMT is given as what is called 150 millivolt. Okay, that is the modulating signal amplitude. Now, if you see here, the units are kilohertz per volt multiplied volt. So it got the same unit as kilohertz. So somebody has asked me this question. Now it is very clear. I asked to wait. So once we've understood the concept of instantaneous frequency, which we are discussing now, and through this example, so the unit of my frequency deviation is kilohertz per volt. That is something you have to keep in mind. So once you know this, this is a constant, but the frequency deviation constant. That means how my frequency is changing per as per the amplitude of the carrier. Okay, so kilohertz per volt or hertz per volt. So it is a frequency deviation. Okay, so that's why the unit turns out to be the same. And so we have to be very careful to use the proper units here. Okay, now if I use the proper units, you will see this is in hertz, this is in hertz, kilohertz per volt, and this is in volt. So everything is there. So you have to just convert a volt into millivolt and so on. So in this case, my frequency will become, so I convert into, sorry, everything into hertz because that is very important. So this becomes 100 into 10 to power 6 hertz, and this also becomes equal to 30 into everything we convert into this one, because somewhere it is hertz, somewhere it is this one, and VMT is 1 megawatt. So my FMT becomes is 100 into 10 to power 6 plus 30 into 10 to power 3 and 150 into 10 to power minus 3. So I can also change into 150 into 10 to power minus 3 volt. So this is in hertz, this is in hertz per volt, and this is in volts. So this will cancel. So now somebody asked me this question. So it is very, very clear how we define the deviation constant. So this I made it clear. So this becomes the frequency of the resultant FM wave. So answer is this one. Okay. So I would rather specify, because this was asked. So unit of KF is hertz per volt or millivolt or whatever you call. So this is one example. Let's take one more example just to finish off this part. Let's take one more example. So I have a signal, modulating signal or message signal, which is given as VMT is equal to 10 to power 5 cos omega mt. Okay. And this modulating signal is frequency modulated. That means FM on a carrier with the frequency of 90 megahertz. And the deviation constant is 5 hertz per volt. So now the question is, I have to find what is the maximum frequency of my FM signal, because frequency will change now here. Okay, so in this case, if I have to find the solution, it is very simple. Just look for what has been given and what has been asked. So solution, if I have to find, I use the same expression, f of fmt. So that's why I taken this example separately, frequency part, just to make the units very clear, kfvmt. Okay, and I have to find the maximum. In the previous case, I just found the relation. Now I have to find maximum of f of fmt. Okay, and which could be given as fc will remain the same, neither maximum nor minimum, and kf, but where my this thing is maximum. What we have given this, fc is given to be 90 megahertz, so I put it in immediately into hertz. Okay, what else we are given is that vmt is equal to 10 to power 5 cos omega mt. No frequency is given here, so I have to find the maximum of this one, so which will be given by this one. So I need to find f of fmt, the maximum value. Okay, because if you recall, the maximum value is given by this. Okay, so let's say I don't put in the bracket, I put it like this, maximum value of that. Okay, so this is the maximum value we have to find. Okay, so I put it here also, maximum, which is given as this one. So in this case, it becomes 90 into 10 to the power 6 hertz, okay, plus 5 hertz per volt. Okay, so I just put the units also for your clarity, and into 10 to power 5 cos omega mt, maximum value of that. Okay, so this becomes my this one. So I can solve it again. So it becomes 90 into 10 to power 6 hertz plus 5 hertz per volt. Okay, I am putting the units also, so it becomes very clear. And maximum value of cos is 1, so it becomes into 10 to power 5 volt. This will cancel. So basically I got is something 90 into 10 to power 6 hertz plus 5 into 10 to power 5 hertz, which means I can find out it is 90.5 megahertz. Well, that means 10 to power 6 hertz. Okay, so that's how. So maximum frequency will be given by this one. Okay, because the maximum value of cos could be the one. So in this case, my answer will be like this. So what we have understood, yes, units are the same. Yes, that was a very good question I was saying. And because of that, I have to take this example and I have to take the concept of frequency because of that question. It was really a good question. Okay, so now we see, and it is one good thing you have to keep in mind. Put the units also. So you can never go wrong, because as I said, we'll be playing with megahertz and kilohertz. One frequency is very high carrier, another frequency is very small modulating frequency. So we speak in terms of kilohertz, megahertz, like that. Somewhere we are speaking in terms of volt, somewhere we speak in terms of millivolt. So put the right units and then you can never go wrong. Like here, 90.5 into 10 to the power 6 hertz, I could go wrong if I would not have taken into the accounts properly. So this was a general concept of FM and all those things. Modulation index, which we have just defined, how these things are related to my delta and other parameters, and how this depth of the modulation matters here, just like what we have seen in the case of AM, that we discussed in the next class. And we'll also discuss my this other parameters and the bandwidth of the FM signal. If you recall, the bandwidth of the AM signal was twice of FM, just simply the twice. If I talk about the AM signal, means double sideband, no suppression of the carrier. So if my maximum frequency is 5 kilohertz, bandwidth requirement is 10 kilohertz. But here, what is my bandwidth? What is my modulation index? Just like we have seen in the case of the AM, we have to understand that, and that we'll do in the next lecture. Okay. So any other doubt before I leave? So I will share this PDF file and the recording. PDF file, I can share it right now immediately. Recording takes a bit time to get processed and other thing, which I normally get after 1 hour so that I will upload later. So again, those who joined later, please note that I have shared all my lecture video recordings as MP4 files, which are very high, huge files, 2 gigas or so. I
Sir,
appreciate that you download in your laptop and my
sir,
PDF file. Yes, yes, please.
sir, which one is better, AM or FM?
AM or FM? I will come to that. Wait. Obviously, FM is better. Why it is better? Wait for that. First, you have to understand the concept of FM. FM is much better. That's why nobody listens to AM radio. But FM is, see, now just look into that. When we used to have AM, Vivid Bharati and everything. Okay. The same Vivid Bharati station got broadcasted from Delhi all the way to Tamil Nadu, Madras, and Chennai, everywhere. Okay. Because the, AM actually you can generate large amount of power because it's a low frequency. But FM, it is at a high frequency, megahertz, 98.3 megahertz radio Mirchi, and it is difficult to generate a large amount of power at higher frequencies, and even milliwatt power at 5G or something like that. That we have so many towers there. So now what we do here, I can't broadcast to the entire country, but like Radio Mirchi has bought a frequency 98.3 megahertz. What it means? That means wherever you go, your Radio Mirchi, the frequency is the same, but the delivery of the content will be different because power is less. You can't transmit to a large distance. So this is the disadvantage of FM, that you need different FM stations for different broadcast stations, but at the same frequency. Like Radio Mirchi has bought that particular frequency. Okay. But what is broadcast in Delhi and what is being broadcast in Ahmedabad or what is being broadcast in Mumbai are different. Okay. But AM is the same. But there are big disadvantages of the AM, which we are going to understand. So just wait. We have to understand the mathematical concept first, which we have discussed today, and we'll let you know. Yes, the advantages are there, you're less noisy and all those things, which we also understand. So just wait for that. I'll come to that. Any other question? Any other query? Okay, so I will share this file as PDF file and look. Now you can actually start looking into this thing. Keep your notes also along with you, or any other material you find in any of the materials you have access to that. It is a very basic concept of the communication systems, very first course on the communication system. So you can get many things from various places. So just go with that. But yes, as I said, various books use different nomenclatures, different symbols. What I am used is more or less the very conventional systems, nomenclatures like KF, MF, or delta. That is a general nomenclature terms which are widely used in various books. So I stop the recording here and I stop the presentation and share these slides with you. Okay, then. No other question, nothing in the chat box. So we'll discuss and extend this in my next lecture. Okay.